for joining us once again for one of our ad hoc webinars. On electricity markets, I'd like to first acknowledge the traditional owners of the land on which we stand, the people of the Kunal Nation in Victoria. I'd like to pay our respects to their elders, past, present, and emerging, and extend a particularly warm welcome to any of them who may be attending today. For those who don't know or haven't met me yet, my name is Guillaume Roger. I'm an associate professor of economics at Monash, working specifically on electricity. And I'm very pleased to welcome Professor Gregor Zöttl from Nuremberg. He's sitting right there. This is a fake background, I'm told, because he's actually home. He's not on campus these days. But we're very happy to have Gregor address us from Nuremberg in Germany to speak about the implications of market design on transmission investments. We're going to start right away. So over to you. Thank you.
So very good. Thanks a lot for the super kind introduction. And thanks a lot for having me and spending your time sharing my ideas and my research. I hope you can see my screen now. Everything is fine. So I would just proceed now.
Absolutely. Go right ahead.
So the title of the presentation is The Impact of Market Design on Transmission and Generation Investment in Electricity Markets. Actually, the main focus of this work is to look at the market design in electricity markets in the long run, where we have big challenges. For example, in the European and the German system, how to coordinate in the long run proper placement of generation investment, and also the closely related network investment issues, which somehow have to be such that the whole system properly works. Yeah, and so especially in Germany, we have the following challenges. We are abandoning nuclear. We are in the long run planning to abandon coal and lignite. And this should be replaced by renewable sources, and clearly they will be located totally at different locations than the original plants. Yeah, and this calls for strong reorientation of the power network, basically. Yeah, so as you might know, and as it's also the case in all other liberalized electricity markets, is the networks are regulated. So there's the government who is organizing network expansion, is planning the network expansion and allowing for certain network expansion plans. You see this on the right-hand side, network plans, which are then implemented by the transmission network operators. Yeah, and so what we want to have is market design that properly organizes network investment and private investment and placement of new and green or green air production facilities throughout the country, basically. Yeah, and how to model and analyze this. That's going to be the core of this presentation of this research agenda, which I want to briefly present to you. Yeah, so the important thing is that indeed here's just for confirming my statements. Yes, this was one study of a German energy institute, which indeed show that network links are under stress in the future and also currently, and so we need this type of reorganization and investment issues, basically for the network and the related proper placement of generation facilities, and maybe also in smart placement of demand, demand side management, which clearly is much more complicated. You don't want to move big car producers or whatever to totally different places. Yeah, or consider Tesla, which is now being placed in the region of Berlin, a huge plant. Yeah, so it would have been difficult to convince Elon Musk to just go somewhere else because there's better production situation of electricity. Yeah, so that's going to be the issue. But what are the main questions we have in mind with our agenda? So what impact do in a zonal electricity regime? I guess it's somehow similar to what we have in Australia, but still there's a lot of differences. So how to charge network fees, yeah, on generation investment, yeah, and what is the impact on generation investment placement and the network expansion? maybe also, but this is something which is very intensively discussed and not very easily implemented in Germany or Europe. What would be the the impact of somehow also adopting the transmission management regime, yeah, to introduce more price zones in Germany, yeah, or to have even nodal pricing, yeah, which is totally out of discussion in Germany and Europe right now, yeah, and how this feeds back on long-run investment, yeah. And finally, I will also present you some results which we just obtained. If we include into this modeling approach electric vehicles and their charging strategies, yeah, clearly that's one part of the consumption side, and so we will also see something there. Yeah, how do we approach those questions which we have in mind? I will present you so-called computable equilibrium frameworks, yeah, which allow to take into account incentives of the agents involved on the one hand side, but also allow to really calibrate and numerically compute with real world data the resulting market outcome or predict market outcomes, which allows to talk about network fees or the different ways of second best market designs regarding transmission management regimes, for example. Yeah, and so based on this framework, which I will briefly illustrate and discuss, we will then really go to market data and then see what different types of market design, what would be their impact on market outcome, on overall system cost or total welfare, however you want to frame it, how large those impacts would be. Yeah. Okay. There's basically the main contribution, which is also the title of the seminar, is basically on this recent publication together with Veronika Grimm, Bastian Zöttl, and Christian Zöttl. Yeah, and then there's two further articles which I will discuss at the end. So the main points which we are making there, since they're closely related to what I will present to you in this main part of this presentation. Yeah, and so briefly, just some idea how to fit what we're doing into the general literature in the field of energy economics somehow. Yeah, just to give you some idea where you should fit us, yeah, with the approach we are presenting now. Yes, yeah, so we have a huge literature which I would frame it theoretical economics, this classically theoretical industrial organization. Yeah, so Jean Tirole, so the Nobel laureate, would be a good example of having a lot of very interesting papers in this field. Yeah, so you would in general model with theoretical approaches, you would model economic interaction. You would then very often get some lemmata theorems which provide general this is better than that, yeah, results. Yeah, and for the specific case of investment and also spot market operation in electricity markets, we have done some work, and there's also lots of work by Andy Philpott, I guess, which is from Australia, and many others. Yeah, so I was somehow focusing on some Australian guys here in this part here. Yeah, and basically those theoretical analysis derives typically general properties of those market equilibriums on a suitable properties. Clearly, what those studies, if you don't further use those for a computational analysis, equilibrium analysis, you can very well take into account objectives of different agents. All that is very nice, yeah. But what you won't get is to get a exact or a realistic quantification of trade-offs which we observe, yeah, or how much better is this than that. Yeah, so this is typically something which is not obtained, but which we are doing by using this computational equilibrium approach, which I will discuss in a second. Yeah, there's many other articles which rather come from an econometric statistical perspective. Yeah, they would use past observed market data. Yeah, and typically what they do by statistical econometric tools, they typically do a very good job in determining the impact of changed market design. Yeah, but clearly, yeah, and even they don't even need to make assumptions regarding the objectives, profit maximization or utility maximization of the different agents. They since they observe the market fundamental data and also the outcomes, so they don't need to make modeling assumptions in this context, yeah. And so they can very well determine the impact of changed market design, but clearly it's limited if you want to look very far into the future and look at new market designs, new market rules, which have not been there in the past or in comparable situations. This approach clearly is not helpful in this direction, but it's very helpful, as I told you, to just see what was the impact of observed market design or observed market rules, but it's not so good in looking far into the future. Yeah? There's better to have models, yeah, and computational models. And so one perspective is you rather try to calibrate the overall energy system, and you determine something which is called overall optimization analysis, first best analysis. So there's lots of, so it's a single objective optimization problem where you realistically calibrate all the costs which you have from production, from investment, from network expansion, and you put all this into one single objective function and you maximize this, yeah, and then you get, there's many interesting contributions there, and so this helps you to determine an ideal benchmark. So meaning if the market would work ideally, all the agents behave perfectly competitively, there is no distortion due to fees, the market design is ideal, blah blah blah, then this helps very much to tell you where you could get, this type of single objective optimization problem calibrated with realistic market data. Right? If we go one step further, we have something which we call computational equilibrium analysis. There we again use optimization tools, but we would take into account that there is different agents involved in the market. For example, the private firms investing in generation facilities, the government planning together with the TSOs, the network expansion, and we have different agents with potentially different objectives there. The different objectives due to market power, due to market rules, such as zonal pricing, which are not perfectly aligning those objectives. And this is when taking those different objectives into account and modeling and solving this for realistic market data computationally, this is basically the domain where we are contributing. And also there's many contributions in this context, And so our new perspective, basically, with this strand of literature, this contribution which I'm presenting today, is basically to have, for a system of zonal pricing as we have it in Europe, to have those different agent perspectives in a computational equilibrium analysis. That's basically where you should locate what I'm telling you today, basically, in terms of literature. And we are also, as a benchmark, determining within our context this welfare optimal benchmark, this system optimal benchmark, but we are additionally, and as a main focus, solving for this equilibrium problem for real world calibrated situation. So roadmap of this talk, we are done with the introduction mainly. Before I will directly present you the computational equilibrium framework, I will not have too many formulas for this presentation today. As I was told, it's rather a policy-oriented seminar. I will first to give you the main ideas what happens in this zonal system. We will have a very simple two-node illustrative example to see what could be some of the trade-offs, which will show later on in the fully calibrated model. But it's so this should give you an idea, and then I come with the framework and with the calibration and the results, basically, and then finally the extensions of those two other papers. Good. So what's the main trade-offs which we're going to see when we employ the fully fledged model? So consider a situation with two nodes. Just two nodes. There's tons of production facilities somewhere here, wind, coal, whatever, in the north, and there's one transmission line, and for whichever reason in the south, maybe there has been some dismantling of nuclear power plants, there's a lot of consumers sitting, but there's very few production facilities, and and all this is one price zone. This is how it is in the German market. This is one price zone. So at the day ahead spot market, we have trading, and those power plants, they can supply the entire demand in whole Germany. And prices will be dominated by those plants. And in principle, there will be a lot of production by those guys in the spot market. But in reality, this line is not enough. So we have 5,000 megawatt hours which can be transported, and 10,000 should be consumed in the south. And there's 3 options. Either we just say, okay, let's not supply those customers. This would maybe amount to a loss of 10 billion. We could build an additional transmission line, which would be better than just ignoring those customers. And the third option would be build a gas power plant. Build a gas power plant. And from a system optimal benchmark, if you would just run a single objective maximization problem here, we don't need to run it, we can just see it. It's a super trivial example. System optimal benchmark would clearly indicate us, okay, the best thing to do, build this plant here in the south, and we're done, and then we are having 2 billion of costs for this. And so that's the best option to take. So this would be the system optimal benchmark. And now the issue is that in the zonal system, we will not reach the system optimal benchmark. We will get some type of market failure due to the market design. Why? As I just discussed, at the spot market, those if there was a plant, for example, a very efficient gas turbine plant, it would likely be at higher cost than those cheap production facilities here. And this would mean that at the spot market, it would not earn any money. And all those plants here at the spot market would basically supply or trade at the spot market. And this would mean that just the spot market result would result in overloading of the line, basically. So there would be 10,000 units being sold from north to south, but remember, the line can only get 5,000 being transported. And so there would be a problem. And so basically, once the spot market closes, the TSO in a redispatch action would need to take into account this problem, meaning he would need to shut down some of those trades from the north, and he would need to make a phone call or some formalized procedure with those potentially existing plants in the south to tell them, okay, guys, we need you. We have a network problem. We need you. But what happens in case of cost-based redispatch, that's the case in Germany, those plants would not earn any money beyond their short-run variable costs, basically. And so that would mean they would never make money if this would be the standard situation throughout the year. They never earn anything in the spot market. And so this type of situation would mean that so this would be the redispatch situation. So you cannot trade here, and so this plant here in the south can never expect to earn any money beyond short-run marginal costs. And so since those are private investors which have to earn their money in some realistic way, private investor would not decide in this situation, would not decide to build a plant in this type of setup. So they would not decide to build a plant in this type of setup. And because it would be quite clear, if I decide to build a plant today, I will never get my investment back. I will always get whenever I need to run, I will earn my short-run marginal cost, but all the investment will be lost. And so no reasonable investor would do this. And so the only solution, basically, when it comes to planning the network expansion for the government, government together with the transmission system operator, would be to say, okay, we know there's no private investor investing a power plant in the south. So we've basically we're left with 2 options. Either we just disregard the demand in the south, which is a loss of 10 billion, or we build the network for 2 billion. And what we have, sorry, the network for 5 billion, And all we can do is basically build a second network line, because we know the best option, this plant located in the south, will not obtain in the market environment. Yeah, so that's the problem. Yeah. What is solving this issue is if you have price zones taken into account at the spot market. Yeah, then prices in the south already at the spot market might be higher, and the plant in the south, the owner knows that for some hours throughout the year, prices will be way above maybe his variable short-run cost, and he has possibly the possibility to earn back his investment. So there the situation might be different. Yeah, when we later on talk about cutting the single price zone of Germany into several zones, this will be the effect which plays a role. Yeah, and so. And if we observe then the plant being built in the south, that means we don't need the super expensive network expansion. Okay, so this is the effect how we could say for network expansion. Clearly, there might also be other ways, also for a single zone, for example, to have regionally differentiated network fees. Yeah, assume, for example, that you determine as a regulator and as a transmission system operator that plants which are located in reasonable zones, in reasonable regions of your unique price zone, have to pay maybe much lower network fees. Yeah, what we later on will call G component. Yeah, that might induce them maybe to anyhow be more inclined to build a power plant in those regions, yeah, production facilities. Yeah, so it might also be to obtain a similar effect if you have different incentive schemes, yeah, which induce power plants to be located in certain regions. Yeah, we will also discuss this. Yeah, instead of having two zones, you might also think about regional differentiated network fees, which favor those regions, yeah, where you desperately want to have production facilities. Yeah, and so bypass basically this price zone organization. Yeah, okay. So this would be the simple example. Yeah, and now we go to the framework. Yeah, to the mathematical framework. Yeah, so the setup is as follows. We have basically from timing, we have a transmission investment. This is made by a social planner. Yeah, then there is generation investment made by firms. Yeah, and afterwards there's the spot market trades taking place for many consecutive hours. And in case the spot market trade does not deliver the results which are compatible with the network, then you need redispatch being organized by the transmission system organizer. Yeah? Okay, so that's the idea, and each firm can invest in many technologies which come at different investment costs and variable production costs. Yeah, so we have cost-based redispatch, and we look at market splitting, as I just said. Yeah. So what is the TSO facing in terms of cost? He's if he decides on network expansion, he's facing network expansion investment, and he's facing the cost of redispatch. Yeah, and when we talk about the network fees, yeah, clearly the TSO is not supposed to make any profits. We assume it's the TSO is ideally regulated, so we don't focus on this regulation games or whether they can escape regulation and so on. We think that the TSO is ideally regulated, so it's totally aligned with public interest, and we could look at energy-based fees which are paid by the customers, yeah, to recover all those costs of the TSO, and we will later on also look at location-based, location-specific, capacity-based fees paid by generation facilities, yeah, somehow maybe to induce them to locate at proper sites. Yeah, that would be the idea. Yeah. And so if we have come to a graphical illustration to our three-level model, yeah, so we have on the upper level, we have a social planner. He basically determines network expansion. Then we have here the generation investment facilities and the trading at the spot market. And finally, there's again the social planner deciding on the renewable production. So this would be the scheme of the coupled optimization problems basically. Yeah, so the network expansion would maximize social welfare, yeah, by choosing basically all those variables, yeah, And when optimizing the network, you would anticipate both the spot market equilibrium, and the investment of firms, and also the redispatch you would need to do later on when you encounter network problems. Instead of having a single objective optimization where we just optimizes the system, we now have the different agents. So the network planning, the private firms here choosing the investments and doing the spot market bits. And finally, it's again the redispatch stage, so the social planner who chooses the redispatch, leading to additional cost. And so basically, this is the most formal, most formal slide I'm having in this presentation today. So don't worry for that. So this is a three-level problem basically, and in our articles we show that we can reformulate this such that this can be solved in a computational way in the end. But I don't think we want to deepen. So we can reformulate this minimization problem to become a maximization of welfare problem. And so this can be reformulated later on. So this is basically the core model where which takes into account the different perspectives of the different market agents, and which allows us, for example, to look at fees and taxes and network fees and capacity-based network fees, because here we're explicitly focusing on the objectives of the firms who make the investment decisions. So this is why we can talk about fees. Basically, we can talk about fees and so on, and we can talk about price zones and all these kind of things. As a benchmark, we will be also looking at something which we call a system optimization first best benchmark. There basically there's a social planner who would maximize everything, the network expansion, the capacities, and the final transportation through the network. And this would be a single objective optimization problem. And here from the lower levels, for illustrative purposes, I didn't cancel those boxes, but basically just the maximization problem. And here we've all the constraints listed, the mathematical constraints, which refer to production facilities. So how much wind can be built at certain locations, how much combined heat plants can be built at certain locations, which network links can be built between which nodes, how can the scheduled production really be transmitted through the network. All those constraints here would be one page. If you read an article, it would be one page of constraints. Basically, how would, and here's they're just summarized. But all this is basically only taken together, disregarded that there's different agents taking the investment decision, the production decision, and just maximize the overall welfare. It happens that under idealized condition, this corresponds to an idealized benchmark of nodal pricing and so on. But we will mainly refer to this as a system optimization benchmark. And now we take this model. In principle, it's 3 pages of formulas and even more. So, but I decided to not bother you with that. We've only 45 minutes basically. So I'm giving you this graphical representation only. And now we take this model and we take it to the data basically. So we as I told you, the plan is to look at network to recheck or to use the data which is used for the network development plan in Germany. So there's all the scenarios are well defined, the input parameters are well defined, and then they come up with candidates and desired lines which should be built by the transmission system operator. And so we are basically mainly referring to the data which is in this plan, but this development plan, which includes demand values in Germany, import and export to the neighboring countries. There's certain assumptions regarding how much wind and solar production will we have in. So this is a prediction for 2035. Will we have in 2035? Which power plants are sitting at which locations? Which which renewable plants are sitting at which locations, which costs do they have, which investment costs do potentially new build power plants have, and all this kind of data. Yeah, so we fill this all into the model, yeah, into this basically 3-level optimization model, which we can reformulate to be easier. Yeah, so but we don't want to be too detailed on that. And so this is basically the input data we use. Yeah, and additionally we look at all the candidates which are discussed for line expansion. Maybe, sorry, one more thing. And we assume, and this is a strong simplification of our approach, yeah, as compared to reality, we assume that each of the regions here in Germany, yeah, this Bundesländer, it's called Bundesland, or it's yeah, country, state, yeah, I don't know how to translate this perfectly. Yeah, it's the different states of Bavaria, Baden-Württemberg, Berlin, and also on. Yeah, and so those are assumed to be one node, and we have only the links being represented as single links within those, or between those different states of Germany, basically. Yeah, and that's basically our network which we use for our framework. Yeah, and so now they're here. Maybe here you can even see this better here. The dotted lines here, those are the transmission expansion candidates which are indeed discussed for being used in the for the German network development till 2035. Yeah, and so those will enter as integer variables into our optimization problem. Yeah, so this network development can pick certain lines, yeah, and so there are certain corridors, and in total we have 15 line candidates, and there's a certain lump sum capacity how you can build those lines. Yeah, so there's 2 gigawatt. If you have those DC lines, yeah, those high voltage, those high voltage DC lines, there's certain minimum capacities you can build those. Yeah, and so there's in total 15 candidates connecting our which can be additionally built within our algorithm. Yeah, so that's the idea. Yeah, and so now we look at different market designs, and scenarios, and we will refer to those throughout when presenting the results. So ME is market equilibrium. Yeah, so ME is it's all most of the stuff here is ME is market equilibrium, and the index is indicating the scenario. SQ would be status quo. Yeah, that would be basically for the current situation. You have a single zone in Germany. And we have the current planning of the network development plan. This would be how much lines would be built. This would be the system cost or overall welfare, basically. As compared to that, we can also determine some system optimal benchmark. Yeah, so basically disregarding all the different agents, just saying, okay, if there was a central planner in Germany who would determine optimal transmission investment, optimal plant location, optimal dispatch, everything optimal, how far could we get, yeah, given the assumptions of our framework? Yeah? So basically, this somehow will tell us how far could we get, how much could be gained by doing reasonable market design. Yeah, and then those adjustments here are suggesting a different amounts of intervening into the current market rules, yeah, and so I separated those into moderate adjustments, yeah, because what happens in Germany, we are currently, when building our network, yeah, so this network development plan, we are assuming that all the green production which is in the system is forced into the system. Yeah, so we always have to, and there's no way at the planning stage to decide that the green production will really be cut at some extreme hours. Yeah? So basically the network expansion is always made such that we can really digest with the network all green production which is predicted within the scenarios of the network development plan. Yeah? Second thing is the network is also planned in a way that the redispatch, which can take place clearly, yeah, is not is not taken into account at the planning stage. At the planning stage, we are saying, okay, those will be the spot market outcomes, yeah, and we want to have a network which is able to digest all this, yeah, and so those would be two things to advise government. Or we did that, yeah, and in an applied study, yeah, and so those would be two small things which would not really affect true market design, but they would just affect the way how this network development plan is indeed computed. Yeah, so basically in the down somewhere in the engine room of doing this network planning. Yeah, so allowing more flexibility at the time of planning the network, yeah? Anticipating that later on you will be able to switch down green electricity, and anticipating when building a network that later on you will be able to do redispatch. Yeah, and there would be more drastic adjustments, which we also looked at. Yeah, so this would result in what would happen if we would separate Germany in price zones. Yeah? For example, 2 different price zones, yeah, such that the short-run prices already reflect the spot prices already reflect investment incentives. Yeah, and or look at different G components, at different investment network fees for generators, for investors, such as to incentivize them to locate at more reasonable locations. Yeah, those are the scenarios. So, and this is what we get. Yeah, so here we see on the right hand side we see the different lines on the status quo. Indeed, yeah, we take the welfare there as a benchmark welfare. Yeah, and we see that in the status quo, indeed, there is 14 lines which are built. That's roughly what is currently planned in Germany. Yeah, that is roughly planned in Germany. Yeah, and if we go to the totally other side of the medal, so this social planner optimum, we see there's 1,500 million to be gained per year. Yeah, and we could be much more efficient in having less lines. Yeah, and having much less lines, and having much higher welfare. Yeah, and having also generation being placed at better locations and so on. Yeah, we will see this in a map on the next slide. Yeah, and those moderate intermediate solutions which allow to improve the planning process only of this network development plan show us that we can, if we just would anticipate redispatch and shutting down of green electricity, we could improve a lot on our way to this system optimal benchmark. Yeah, very interesting. We didn't think that we would get such extreme results here. Yeah, so we would get really big impact also of having a more clever conduction of this plan. It would not be trivial because it's a bureaucratic process. It's embedded in laws and all this kind of things. Yeah, but so this would be the result there. And so this is what the status quo here, the lines, the power plants, which would need to be additionally built or dismantled. Yeah, and here on the right hand side, this improved solution, yeah, where we would have green anticipation of redispatch and anticipation of green shutdown of green sources. Yeah, if you look at the specific profile of those green sources which would need to be shut down in reality, we see that it's not many hours where you shut down a little bit, but it's few hours where you shut down a lot, yeah, which help you to save a lot on network investment. Yeah, so and it's unclear what to do with this electricity. Yeah, so if you look at the specific profile, it's not that you can just like produce hydrogen with those within those few hours. Yeah, it would be super expensive to build a electrolyzer, yeah, to run for I don't know, it's 50 hours or even less throughout the year. Yeah, and so this would never be profitable. Yeah, so very likely you have to just not produce this, yeah, and then turn the windmill out of the wind or something. Yeah, and so in total, the total quantity curtailed would be relatively low. Yeah, so this would be clearly something important to see. And what is also interesting is that just cutting into 2 zones the system, now we go to those more drastic adjustments. Yeah, so sticking to the original network plan, but cutting the system into 2 zones or introducing those clever network fees, basically regionally the differentiated network fees has not much impact, interestingly. Yeah? So it could be that the price zones which we exogenously chose were just not optimal and there were weird zonings, but we will see on the next slide this is not the case. And for the G component, yeah, so those clever capacity-based network fees, which should induce investors to locate at proper locations, they somehow don't do the job, apparently because plants are located in the proper locations, but they're not running anyhow at the spot market because they're still not winning the bids in the spot market, apparently. Yeah, so this is also not helpful. Yeah, so those halfway towards some nodal prices regime that does not look super promising here. Yeah? Good, and those would be the first best result. Yeah, so where we have different prices throughout all regions of our system, again compared to this status quo benchmark. Okay, good, and this is the result for the two zones here. Yeah, yeah? So where we have two price zones. And we don't gain much. Yeah. Okay. So policy implications here. So those moderate adjustments, they have a lot of bang, so to say. Yeah. Just having two price zones or somehow trying to say, let's have some clever network fees which are regionally differentiated, does not seem to do a very good job for our setup. Yeah. Does not seem to do a very good job. Yeah. And so we have been suggesting strongly to improve the current NEP process, but it didn't look that having just so somehow two price zones or those clever network fees is really helping a lot. Yeah, a closely related work here. So in this previous what I presented to you previously was that we had just exogenous fixed price zones where people thought it would be a good idea. We've also developed an algorithm in another paper where we determine optimal price zones. Yeah? So basically, so that there's additional optimization running, how the price zone should be shaped optimally if you want two zones or three zones, a fixed number of zones. But the results didn't improve crucially if you just limit yourself to have, for Germany, just two zones. Yeah, they improve a lot in the end if you allow for many more zones. Yeah, clearly, because then you go close to this nodal system, and then it's much better. But if you just have a very few number of zones for Germany, it also, when determining those optimally, it doesn't help a lot. Yeah, so you need quite a big number of zones. Then you go into a good improvement. Yeah. Okay. So actually, I would still have two slides for results regarding electric vehicles. Should I have those for 2 more minutes, or we want to stop here?
No, please go ahead, by all means. I think EVs are very interesting to all of us here.
Okay. So what we have also looked at basically in the setting in a recent working paper which you just submitted, we now introduced in the different regions of our model, we introduced electric vehicles with different degrees of penetration. Yeah, so 1 million, 12 million, 17 million. Yeah, so remember Germany has 80 million of inhabitants, so 17 million is quite something. Yeah, so it's really a huge market penetration. You should expect quite some equilibrium feedback. Yeah, first on the spot market prices, but maybe also on the requirement to build your network. And maybe this also gives you more needs for redispatch, because this more heavily stresses the network. Yeah, because 70 million of battery vehicles, by now they are running on the regular fuel. Yeah? And so the question is, will this maybe yield electricity prices to explode, and we need much more network? And in the end, we have much more coal being burned. And so in the end, there's first on the cost side is a nightmare, and also on the CO2 side is a nightmare. Could be. Yeah. And so the perspective was to address this in the context of our model, basically, in the end. Yeah. So for different CO2 prices, and what was an important levy in this context was looking at different charging strategies. So fixed would mean people just exogenously fixed in the model, they charge at a price of in the evening when they come home, yeah, they charge the vehicle. Yeah? Some charge during daytime, some charge during evening, but irrespectively of the current spot price. Yeah? So no smart reaction to market price. And we compare this to the super smart solution where the people perfectly react to the spot market price. Yeah, and there was also some intermediate solution charging strategies which I don't report here. Yeah, and so what are the main results of this? Yeah? So imagine this is similar framework. Main results. The first very good news was even if you've more battery electric vehicles, yeah, and we take into account that they replace regular fuel vehicles, we come to lower CO2 emissions in all the scenarios, yeah, no matter how you charge. Yeah? So in the end, even though you need to produce the extra electricity sometimes by coal plants or by gas plants, yeah, overall the CO2 emissions drop. Yeah? So that is important. Yeah. So what we have, especially in case of fixed charging, we have very high peaks in the system. Yeah, we need substantially higher gas turbine investment. Yeah, for higher BEV penetration. Yeah, because this was the variable which which could be chosen freely. Yeah, because you won't get more windmills; those are somehow determined by the system. Yeah. What is also interesting, the standard electricity prices, so for people not charging their cars but having an average of the electricity prices, it's not super much changing. Yeah, so the electricity prices in general are not skyrocketing. But if you don't go to a clever charging strategies, your charging prices will skyrocket because everybody wants to charge then in the evening when he comes home after office. Yeah, and so the charging prices, they will skyrocket if you have fixed charging strategies. Yeah, so then we have a problem here. Yeah, so here we have picked now this scenario with the fixed charging, where you have a relatively large problem with wholesale prices skyrocketing, and then we move to the electric car user perspective, yeah, and we see, including all the taxes and the charging prices, yeah, how the charging of a BEV car for 100 kilometers will look like. Yeah, and in total it will be €4, almost €5 for 100 kilometers in 2035. Yeah. And we compare this to the expected prices for standard gasoline or diesel fueling cost. Yeah, and what turns out, the fueling costs, they are lower also for this bad scenario with a non-clever charging strategy. Yeah, they are much lower than for the gasoline and the diesel cars. Yeah, but what you have to keep in mind, this is just the fueling cost. Yeah? So for running 100 kilometers. The game changer of whether it's really cheaper in 2035 to have an electric car or a standard gasoline car will crucially depend on the investment cost of the vehicles. I'm not reporting the slides here, but in the end they make up. So the current predictions for the investment cost, they basically totally eat up this difference here. Yeah? So one has to be careful. Yeah? But in principle, just fueling, there's not an issue. Yeah, even if you have large market penetration, lots of electric vehicles, they don't charge cleverly. Still, it's quite cheap. Yeah, and it's not ideal in terms of CO2 as compared to a smart charging strategy and so on. But it's okay. Yeah, good. Okay, so the conclusions. Yeah, so here I've just summarized what we've seen. Yeah, so we've seen this computational computational equilibrium framework. We've seen that we can model explicitly the incentives of the agents. We've seen that it's that we can work on market design and computationally get how much bang do different market designs obtain. Yeah? So, which is good, yeah, because just to know something is better than something else does not help you so much if it's just an improvement of 2 million and there's 1,500 million to be gained. Yeah? And so we've seen that there's certain slight adaptations which have more bang than just having 2 price zones for Germany. And finally, we've also used this model to look at electric vehicle charging and how is the feedback on the electricity system, including network expansion and so on. Okay, so this was it from my side. I'm happy to take your questions. I see there's something in the chat.
Great, thanks very much. So if you look into the Q&A at the bottom of the screen,
yeah,
There's a question. You click there, and there's a question from Greg Williams that's showing up. Can you see it on your screen?
Yes.
Yep.
Yes. So if I understand your findings correctly, in respect of locational pricing, if we're looking at increasing the number of pricing, it would appear to be much more effective to. Yes and no. Yeah. So in principle, in our framework, so even though we have a model with many agents and taking into account their objectives, we have to limit ourselves to modeling perfect competition of agents. Yeah. So meaning, even if you're in a very small region, you're not trying to push prices above levels of competitive level, and this would push prices above competitive levels, even though you may be one of the only suppliers in this small pricing region at the spot market. Yeah, I should read out the question. Okay, so maybe someone can read the question because it. Can someone still see the question? If I understand your findings correctly in respect of locational pricing, if you were looking at increasing the number of pricing regions, it would appear to be much more effective to go to full nodal pricing rather than incrementally increasing pricing regions. Yeah. So the question is, should we just go to nodal pricing? This is for sure the best. Yeah, it's clearly. And so the ideas in our model, the short answer is yes. Yeah. So the more regions you have, the more efficient you are. Yeah. The more you are. But in our framework, we are not looking at strategic market power. And there is some fear that if you have a very small region with very few suppliers only in one of the zones or at the node, that you get market power problems. And so the short answer, our model would suggest this. You should right away go there, but you would never have this in Germany. This is why we are limiting ourselves to just continuing in this zonal pricing logic, yeah, and checking for some more price zones, yeah. But clearly, if you would have and our model would tell yes, go to nodal pricing, yeah. But there's other aspects beyond the model which might be worthwhile to be discussed, yeah, whether you have market power problems. And actually in the US, then you have bid caps and these kind of things to somehow protect yourself against market power exercise. Yeah, so this might be an issue.
All right, thank you. Any other questions at this time? So can you expand just a little bit, maybe just a touch more on electric vehicles? Because there were a couple of things that you mentioned. One was, there's a price impact because you got more demand for electricity. But on the other hand, there's also potentially a need for network investment. Do you see any actual need for network investments emerging out of your model?
Actually, what happens, because we have so in terms of network investment, you're right, and this is another ideal point of our setup, because what we would need is so in our setup we will always build all the candidate lines which are planned now. Yeah, the problem being that for the current plans of the network, it's not such a huge market penetration here we are looking at 12, but also for 17 million. This is not anticipated the current network expansion plans. Yeah, so basically we're fully using all the current networks, network proposals. Yeah, and so what we would need to invent further candidate lines. Yeah? But then we are somehow leaving the data. And so what happens for all this, for this huge electric vehicle penetration, there's never a way to go significantly below investing in all on most of the candidate lines. Yeah, but we manage with this. Yeah, so with those candidate lines we manage, but it was not possible anymore to go to very low network investment expansion situations as it has been before without those electric vehicles. I hope this somehow addresses your question. Yeah, so we need more network. Yeah, but it's not in an exaggerated way.
So let me just expand just a touch on that then. Presumably, so how did you allocate those electric vehicles? Is it kind of uniformly across Germany, or is it according to demand centers? So the big cities in the south, for example, right?
Actually, for this, so we have those regions here. Maybe let me go here, so we see the setup. So we have those regions. So that's the resolution of our model, and then we associated those 17 million or 12 million according to the inhabitants of those states, basically. Yeah, so there's more inhabitants here, and so we would have this pro rata, yeah, according to the inhabitants of the states, which is easy to observe in terms of data.
Thank you. So there was another question, Gregor, in the Q&A. If you can access it.
So what will happen to considerations for investment in energy-intensive industry, e.g. data center? Yeah, so the question would be, could you consider, so I'm rephrasing this question, and you maybe re-ask if this is not correct. So we did not look at placement of demand somewhere else, yeah, as a response of higher electricity prices in some region. But this would be first interesting. Yeah, so as I understand the question, it would basically be, okay, I want to locate a data center in Germany. If there's regional price signals, is there maybe some motive for me to go somewhere where there's a lot of wind, maybe somewhere here close to the ocean? Yeah, and we have not been looking at this in this framework, but it would be easy to include that. Yeah, basically similar to the electric vehicles, where you put additional demand and you make this demand basically flexible in terms of where do you want to locate it and put it. Yeah, this would need to be modeled and included in this second level, yeah, where there's the consumers are being modeled, yeah, or the firms, and this could be included. Maybe I give some. So in the current market design, if you have a uniform price zone, clearly you would not see the benefits of going here or there with your data center. Yeah, this would only show up if you would either have some specific specific regional exemption to say, okay, if you locate here, you have to pay less network fees, which is not yet the case, or you have somewhat which is related to price zones, and you hope to get lower spot market prices with this located data center, or also maybe some steel production, yeah, which is maybe based on hydrogen, or those hydrolyzers. So water hydrolyzers where you produce hydrogen, yeah, all those location issues right now, they would go anywhere, and we would desperately need this. Yeah, so the issue is super important, that there's no solution for that in the current system, where it doesn't basically matter where you locate. Okay.
All right, we seem to be reaching a lull and the end of our time allocation. So thank you again. Very interesting talk, and was very impressed to see that you can actually put some numbers on this, because you know, things such as nodal pricing, we know some of them like it, some of us like it, and we know why, but now it's pretty clear as to why. So thank you again for addressing us today. Normally we take you out for a drink, but maybe too early for you anyhow. But but
maybe somewhere in the future we meet somewhere.
Exactly. We hope to see you on our shows, you know, whenever Fortress Australia reopens again. Thanks again for addressing us, and I look forward to meeting you in person very soon.
Great. Thanks a lot.
Thank you. And thank you to our kind audience as well for joining us for those talks. There'll be more information coming up soon. Thanks very much, and have a wonderful day for you.
Yeah, for me, it's the day starting now. Exactly. Yes. Okay. Bye.
Thanks. Bye-bye.